nice seminar, but also to come here, stay here for 2 weeks. This is really a great experience. So thanks to everybody. So the story I would like to tell let's start with a theorem which is now almost 100 years old. So Birkhoff in 1927 proved that so on every Riemannian two spheres, two-dimensional, so it's just two with the Riemannian metric, there are closed geodesics. Okay, so for the students, let's recall here what I mean by this. Well, yeah, even if you haven't seen Riemannian geometry, here you can really think about, for this talk, it's perfectly fine to think about a surface in R3, which is diffeomorphic to a sphere. And then geodesics here are just curves. So we can think that this is a surface homomorphic to the sphere, and the metric we are looking at is the metric which is used by the ambient space, which means that geodesics are just curves on my surface with the property that the acceleration is always orthogonal to the surface, right? So it means there is no tangential component for the acceleration. So from the point of view of somebody who's living on this surface, these are really straight lines. These are the straight lines of Riemannian geometry. Okay, these are geodesics, and Birkhoff was interested in closed geodesics. Okay, closed here means that our geodesics goes on, then comes out here, on does something, and then eventually gets back to the same point with the same velocity. Okay, so it goes on forever on this loop. Of course, geodesics, you could also have geodesics, like this, which go back to the same point but with a different velocity. This does not count as a closed geodesic. Okay, this is a closed geodesic. Okay, this is the Birkhoff theorem from 1927, and so it's also interesting for the proof, the method of proof that he introduced while proving this theorem. Because so if you look for closed geodesic on a non-simply connected manifold, let's say you want to look for closed geodesic in a torus, then let's say I use this. So if I'm looking at closed geodesic on a non-simply connected manifold, say the torus, then what I could do is I could look at closed curves which are non-contractible, for instance, this component, and then I just minimize length. Okay? It's easy to prove that there exists length minimizers, and this length minimizer will be geodesic. So of course, here I find the existence of closed geodesic. On the sphere, of course, if you minimize length, the sphere is connected, you just contract to a point. Okay? And Birkhoff argument for proving this theorem was this, that you don't want to it shrinks again to another constant. Okay? The important thing is that in this process, you somehow, precise topological sense, you cover the whole sphere. I don't want to have paths which start from a constant to go get bigger and perhaps contract to the same constant. I want to have paths which start from a constant, they get bigger, and then they shrink again to another constant covering everything. Okay, so this is how path of the loop. On such a path of loop, I can look at the loop with largest vector, the maximum vector. And then I can minimize over all possibilities. Okay, so one is doing a minimax. Okay? And this minimax thing will give you a critical point of the length functional, which is geodesic. Of course, it's not a minimum, but you still find the geodesic. So this was one of the first application of these minimax ideas in critical point theory. From 1927. Yes. 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 And so I do this. So I consider the space of paths in the loop space, which starts from a constant to go back to a constant covering everything. For such a path, I take the maximum. Then I take the infinity over all possible paths like this. Okay? So it splits maximum. Okay? In principle, just an infinity, because we are doing now something on an n-dimensional space of paths. But then you prove that this max is a positive number, and it's actually achieved by closed geodesics. Okay? It's the manifestation of what is called like the mountain pass theorem. You have two minimizers, you have two valleys, and you want to prove that there is a critical, you have a function which has to minimize, you want to prove that there is a critical point, then you look at all paths connecting the two valleys, and you look at the maximum on each path, but then you minimize over all paths, and you get the mountain pass. So hiking on the mountain is what you want to do. Okay, so this is Billiards proof. Maybe it's a bit less known, but it's actually 20 years before this, in 1905. Well, it's station. I've stated this theorem on every Riemannian sphere. There are simple closed geodesics. Okay, so here simple means without self-intersections. Now, a closed geodesic could have self-intersection. This could be a closed geodesic with respect to some metric. Simple instead means simple without self-intersection. Injected amount to network. Okay, so of course this theorem is stronger than the theorem of Billiards. The reason why now not considered building a theorem proven in the rigorous sense is that so yeah, Poincaré argument was not to be Poincaré argument was quite ingenious with this. It was based on Gauss coordination. Okay, By Gauss-Bonnet, you deduce that you have a simple closed geodesic, then this divides the sphere into parts, and the integral of the curvature of both parts is the same. Okay, this follows from Gauss-Bonnet. And then Poincaré equals, okay, let's consider all possibilities which split this field. However, to really prove it's not at all clear. Okay? I think that this can be turned into a rigorous tool, but I think for this you need tools which were developed much later. You need curve shortening flow, which is developed by Grayson. The journality which is needed here, Grayson probably in the 80s. Okay, 80 years later. But with Grayson you can make this theorem, or this argument of Poincaré rigorous. Okay, maybe since we are talking about this geodesic sphere, let's make some pictures. So what are our favorite spheres? One, of course, is the round sphere. Round sphere, we know everything. Here, actually, all geodesics are closed. Geodesics are great. They're all closed. Okay, then let's make an ellipsoid. On an ellipsoid, we also have some nice simple closed geodesics, which we see quite explicitly. And then there is another one here. So the ones which obtain by intersecting with the coordinate axis. But actually, there are many more closed geodesics. This is an example of an integrable Hamiltonian system. It has really big families of closed geodesics. And let's make some more pictures. We have, of course, a surface like this, and it's easy to find a closed geodesic in this neck. Maybe also interesting is this heart-shaped sphere. Imagine that you rotate this heart. Okay, here you would have this closed geodesic. But you also have a closed geodesic here, which is a sort of figure eight. Okay, these are, let's say, pictures of closed geodesic spheres. Okay, then let's move to a more now quantitative question. We know that we do have closed geodesics. How long are these closed geodesics? Okay. Or not to look maybe then at the closed geodesic with minimal length. We have possibly many closed geodesics. We look at the shortest closed geodesic. How long is the shortest closed geodesic? Of course, I have to analyze just to be speedy. And a good way of visualizing is to say area. Right? So or if you want, we're looking at this are raw geometric geometries. I take the minimum, or if you want to shortest closed geodesic. and I want to divide by the area, surface area. Of course, to make them this ratio still invariant, here I have an area, which here I should have an area, which means that it's over square. Okay, this quantity here is called the systolic ratio. Systolic ratio. Because this shortest geodesic is sometimes also called the system. Okay, so every metric has on the two sphere has a well-defined systolic ratio. What can we say about the systolic ratio? Of course, the systolic ratio can be arbitrarily small. If you want, the infimum over all possible metrics of the systolic ratio is 0, right? Because I can, in fixed area, I can find a metric which has a very short length. Like here, the surface area is at 1, but then I have here a very short close to this. So here, the interesting question is actually to try to maximize the systolic ratio. And this is the interesting question. Okay. The setting of the sphere, so this is a question which actually has a long history. It starts probably with Löfner in the 40s, who studied similar question, but not for the sphere, for the two torus. They non-contractible terms. So we are special case of S2. And the first result is so on the sphere, arrange a matrix so that the shortest geodesic is as well as we wish. But also another, also the torus. The torus. So set no matter what, the infimum systolic ratio will always be 0. Unless you put maybe, I don't know if you can get interesting problems by putting, I don't know, some symmetry, something which forbids these kind of things. If you put symmetries, then maybe you put exactly. The thing is, we're fixing, we're leaving an NS2, then we put, I don't know, maybe at the end of this talk, we also move to some branch, but let's say we're on S2, and we are varying the metric. That's why I want this team over G. I vary the metric. And this is what I mean by this. Okay, Kroc proved that this supremo is finite. But in other words, if I consider all possible metrics, let's say, of such that the surface area is 1, then I'm always able to find closed geodesic with length at most some big constant. And then there are lots of work in trying to improve this constant. But of course, what one would like to know is what is the metric which maximizes the systolic ratio? Yes, well, this question is also studied for non-compact manifold. For instance, it becomes interested in, for instance, surfaces. You can consider surfaces which are non-compact but have finite area, like they have cusps. And then it becomes again a very interesting here. No, you can really go into situation. And it's actually relevant. Yeah. The whole theory of surfaces of negative curvatures is very rich. There is actually fruitful to look at also systolic question. There are a lot of results on that. Okay, so let's do some computations. Let's look at the systolic ratio of, I call it, round metric. Round metric just means that, yeah, the usual, the first sphere into here. Okay, what is the systolic ratio? So here all geodesics are great circle, they have length 2π. These have to square, and I have to divide by the area of the sphere, which is 4π. Then I get the systolic ratio π. And of course, the first thing one would suspect is that the round metric is the maximizer of the systolic ratio, right? Geometric problems, maximizer should be really very symmetric things. But a first surprise comes. Let's look now at if G is a so-called Zoll metric. Zoll metric means this. It's a metric such that all geodesics are closed and have this effect. Okay, so the standard round metric on the sphere has this property, but it's a bit surprising. At least when I first heard of this phenomenon, I was surprised. There is a huge space of metrics which have this property. And they have a very old history. They were studied in the 19th century, so in the 1860s, for instance, by Darboux. And so it seems to produce Zoll metrics if you look at a particular sphere, which are spheres of revolution, where you take a curve and you just rotate. What actually Darboux showed, there were 150 years ago, that I can start with any curve line. It has to start horizontally here, and then here does something, then it ends vertically. And that showed that if here there is another curve which satisfies a certain differential equation, which you can solve, has a unique solution. So for any curve here, I can find some way of going there on the other side. In such a way, then I rotate this thing. I obtain a Zoll metric. So all my geodesics are closed and have this effect. Okay, so there's a huge space of metrics. Here there is a bit of difficulty to make things smooth here. To be on the safe side, if you want to make smooth, then the trick is to assume your curve here is spherical, which means that around here your circle looks like around here. Okay, and then you don't have problems with it. But then, of course, in this way, there are lots of examples, but these examples are not analytic because here they coincide with the sphere. The analytic should coincide everywhere around here. Okay? But they're called zone and spheres. But we're never going away from spheres. Spheres. Only spheres. Yeah, it should be, sorry, there is just one condition. It should be the graph of a function from here to here. I cannot do, because otherwise you would, I don't want to create, this tangent is bad. I don't want to have vertical tangents, otherwise I would create geodesics here. Okay, so think like this. At the end point, if you want it to be smooth, if you do vertical, then you get something with a singularity. If you want to be smooth, here you better be vertical, but inside you don't want to be vertical. Okay, so it's a graph of a smooth function. Yeah. The round metric is a solid metric. So the round metric is always the one which, if your curve is the square root of 1 minus x squared, then you get the round metric. But then you can change this and still get the field. Okay? Yeah, that's a good question. No. No. Zoll requires, we say, on dimension 2. In dimension 2, you have Zoll metrics just on the sphere and on the real projected space. Because that's a portion of the sphere and then the standard metric on the particle. Yeah, no, but as soon as you have genus, it's impossible to get this. Okay, so these are all metrics. Where the relevant, if I take a Zoll metric, then the systolic ratio is also pi. Okay, this I think was first observed by Einstein. 70s. Right, I guess the reason is that Zoll metrics, geometrically, they are different from the round metric. However, the flow, the geodesic flow is really different. And actually, it's systolic ratio. Such that the corresponding geodesic flows are conjugate and then they have this systolic ratio. So from the point of view of dynamics, if you're a geometer, a Zoll metric like this, of course, is different from the round metric. If you look at local invariance, curvature, so it's different. But if you are somebody in dynamical system, you look at these two dynamical systems, they are the same. Right? Therefore, they have the same systolic ratio. Okay. Then, of course, if you try to, so let's try to modify this here. you divide this rounds here a bit, then you create, then it's quite clear that this is an equation, right? When you create an ellipse, that one of the geodesic is long, but one of them will be short for the same principle that the average, like qualities between the dimensions. No, ellipsoids have never, well, the only ellipsoid which is all surface is round. All the other ones are integrable, so they have really many closed geodesic, but they have closed geodesic arbitrarily long. Okay? There's a differential equation. I could divide it, but now I'm sure if I write it down, I get it wrong. So, but I can show you it's a simple differential equation which it's an ODE. I write the graph of this. You write this as the graph of a function from x to y, and then there is a differential equation that if you solve it, you get the other graph. Okay. So if you want to look at some other, of course, the difficulty we have now is that it's not easy to forget any metric what is the shortest delay. It's difficult to, even numerically to find to solve this problem. But there is an interesting class of examples that one can look at. These examples are made like this. I take a planar surface, this, and then I think that I have two of these disks. I group them together, and I think that this is it's like a metric, which is let's say it's flat here, and then it turns very quickly. As in this case, it will have infinite curvature around this boundary. So in other words, I have this, but I consider it as a limiting situation. This is the limiting situation in which I have like a flat disk, another flat disk. I put them very, very close, then I join them around in here. Okay. So, what is the advantage of it? They have this they are just straight lines. What does it happen when I reach this point? Okay. Now it will go on the other side. And if you think of it, it will go in the other side in such a way that here, so I'll now draw it this different kind of line to say that the other side. And here the rule will be that these two angles are the same. In other words, this is really the reflection law of billiards. So if you want to understand geodesics on these very flat spheres, you basically have to understand the billiard dynamics. Okay. Okay, and this of course bounces here, and then it's again on our side. So this is our geodesic. Okay, so now that we have this example, let's look at some for instance, if I start from a circle, now this is not the round measure, now this is now the flat disk, and I do this operation. I explain. What is the shortest closed billiard trajectory? Diameters. I go back and forth on a diameter. So what would be the systolic ratio in this case? Okay, so my closed geodesic now has length, so the diameter has length 2, but I have to go twice. So it has length 4. And this I have to square. And then I have to divide by the area. And the area is twice the two values. Okay. So we get 16 and 8 over 5. But 8 over 5 is still less pi, right? Because 8 is less than pi squared, right? Okay, so has a pretty high systolic ratio, but the round sphere is still because so you have many, but you have really many activities, regular activities to action. But the shortest ones are really just and then this is 2 and then okay. But then let's do this. Training. They again same trick. I think now this is equals. But then of course the smooth object of the constellator is everything. Okay. The shortest rules the actually funny things. Right. Surface. No, just and roads, but again, the size of the triangle is fine. So what is the height? Not here is square root of 3 divided by 2. But then I have to run over it twice. So my geodesic has length square root of 3. What is the then I have to double it. Triangle. So it's square root of 3 divided by 2. Right? I can scale up this number a bit, but okay. And there is an open conjecture. The supremum of the systolic ratio on the sphere is precisely this number. And this example here is Kalani and crook. It's called the Kalani crook. Okay. Conjecture is okay. In the last, so we have to. Okay, let's try to. Well, first, on my own together with Abraham and Pedro Salomao, question and have metrics are local maximizers. Of the system equation. So we start from a zone metric, perturb just a bit, and the system equation does go down. I really have to go far from zone. For instance, in the direction of the Scalab crook. Again. Okay. This is actually not an easy theorem, exactly because there is this huge space of zone metrics. So it's not an theorem just improved by want to prove that something is a local maximizing or location demand deliver. Here so here there are some ideas in effective geometry. I mean, the precise if I perturb the metric, is full topology. There is a C2 neighborhood of G. So with respect to the metric, there is a neighborhood that all metrics on that neighborhood have symbolic ratio less or equal, and equality all fit only. This is possible. This is possible. This is possible. Then another result that we have is that zone metrics are global maximizers, but among peers of revolutions. If we have the symmetry, again, but let me one conjecture. Yeah, I will probably so my point is that closed geodesics on the sphere, there are not on the sphere. And the reason is, okay, we're looking at closed geodesics on the sphere, but actually the space where the geodesic, so in order to determine a geodesic, I need to give you an initial point and also an initial velocity. Okay? So the free space of the geodesic flow is the unit tangent bundle of S2. These are the vectors, tangent vectors to S2. We can say with unit norm, right? Because we can always think that our geodesics are parameterized with velocity 1. Any difference to change velocity. Okay, S2 is instead this space here, this is now it's a three-dimensional, right? I have for every point I associate an S1 of direction. This space, what is the topology of the space? Anyone know? Unitangent bundle S2. No, it's not S2 because we are putting this condition. If we were putting the whole thing, then it would be a rectifier. But we're putting this. Let's do this. So how do we determine? Let's do it for the round metric. Then, of course, the topology will not depend on that. So how do we determine such a unit vector? I have to choose a point on my sphere, meaning that I have a first vector 2, and then I have to choose a tangent vector. The tangent vector is the ground sphere, vector which is orthogonal. And then I can put it here. So my unit tangent space of the sphere is associated to pairs. These are pairs of orthonormal vectors. Then if I have a vector, another one which is orthonormal, and here I write the vector product, I get a 3x3 matrix uniquely. So this is an orthogonal matrix with determinant 1. Okay? So this is orthogonal matrices with determinant 1. It's SO3. What is the topology of SO3? Well, this is not simply connected. The fundamental group of SO3 is CO2. Okay? Which you can prove it in several ways, but I also got the favorite proof of this start. Maybe some of you have seen this from Dirac band. Well, I didn't see that from Dirac, but I see the idea, let's say, from Dirac. Okay, I want to show that the Y1 of SO3. So let's do this and then we can stay using it. Okay, so I think of this as SO3, right? These are rigid rotation. So, but now I want to look at parts of rigid rotation. That's why I'm using a band, because I will do some, let's say, this part here I keep it fixed, this is the identity, and this part I can rotate. And this will be now a path of rotation. The belt is my path. Okay. So this is just the trigger path. It starts from the identity, arrive at the identity. If I want to do one full turn, I have to twist this twice. Okay? I rotate it by 2 pi. The front here is the end in front of me. And now if I want to untwist, and then you can do whatever you want. But you cannot untwist. Okay? But now also, this means that Y1 is not. But now let's do one more twist. So let's double this. So one more. Okay? And now miraculously, let's redo it. Start with this. One twist, two twists. Okay, now it's okay. So let's now state then the conjecture. So once as a curve, it's either contractible or not. Some closed geodesics are and some not. And for instance, these rates here are non-contractible, right? So this corresponds to one solar rotation. It's the non-contractible field. Then here, one could define the contractible systolic ratio, which is the same thing, but I look at the minimal length of closed geodesics, which are contractible in T1S2, when listed there. Again, I square it and I divide by the area. Okay, now this is a different thing, because for instance, in the round metric, all my geodesics, I just run once over them, they are not contractible. But P1 is T2, so I have to run twice over them. So here for the round metric, for instance, I would not get length 2 pi, I would get length 4 pi. Okay, so it's a different thing. And here the conjecture is the conjecture which is to Alberto Abbondandolo. I mean, I have a closed geodesic. A closed geodesic, if I look at it not on S2, but I look at the velocity vector, I look at here, I want that in this space, it should be a contractible closed loop. Because in this space, the fundamental loop is V/2. So we have two kinds of loops. Loops which are contractible and loops which are not, but then if I do them twice, they become contractible. Yes, this is the loop given by all the tangent vectors. Yes. The conjecture is that all metrics, so including then of course the round metric, maximize rho contract. Evidence for this conjecture is that I said here now for the round to sphere, the strength ratio is bigger, it's 4 pi. And if somebody is interested, then I can compute for you the contractible strength ratio of the Calabi-Croft triangle and it's smaller. So the Calabi-Croft triangle is not a complex number. But still, this is not a conjecture. I mean, I should plot by Scalange to this data. This can be a postdoc at our university. But in general, it's about the conjecture. Okay, then yeah, sorry for going over time and much for your attention. Well, we are contractible one with sometimes it's depends. of Japan. Round geodesic are great circles. Great circles, it means, right, that proof prediction. Great circle. Let's do this. So my point, the vector u, is turning one thing here, and the velocity vector is doing like this. Okay. If you think for a moment, this is precisely the model SO3. It's like in SO3, you really take one loop of rotations. Okay, the one twist, the 2-pi twist, but this is non-contractible, as the Mahler showed, which means that this geodesic, this is not a geodesic which is counted by this experimentation. If I want to see, I have to go over it twice. But then if I go over it twice, its length is not anymore pi, it's 4 pi. And I have to square it and then divide by the area. And so now I get 4 pi. This is the new calculation. Okay, and then exercise. Compute contractible systolic ratio or the metric given by this Calabi property. Very young.